Right. Pupil tracking and its applications in mouse control. I'm Aaron Rogers. This is Thomas Carroll. All right, so past research into eye tracking. Most of the research has been using infrared because of the advantage through the bright pupil and dark pupil technique. When there's a camera and there's infrared, the pupil will illuminate or be very dark, really easy for image processing and tracking. There's been hardly any research into optical cameras because when you use optical cameras, you have glare through just any visible light. You have issues as color come into play, and really, it's really the glare that's the main problem. I'll get into our setup, but a lot of them try to use the camera on top of the monitor, like your traditional laptop webcam setup. And that's very impractical unless you have a very high resolution camera due to the low resolution, which first group pointed out, like they had, what, 5 pixels for the whole length of the eye? That's terrible. So yeah, low resolution. And also, other approaches that we read were very slow. So we tried to aim for something that would be somewhat real-time application. Right. So our equipment, we have our National Rifle Association baseball cap fitted with our, wait, how did it go back? Okay, anyway. Fitted with our Logitech webcam so that it gets a close image of the eye. And we used nylon zip ties, took a knife, put some holes in it, and that was it. All right, you want to talk about this?
Sure. Okay, so after we capture a picture of the eye, we have to do a few image processing steps in order to find where the pupil is looking at on the screen. So the first thing we do is we take a threshold. We use about, if I use 40 and below initially, that's 0 to 255, 40 and below, to get where the pupil is. And this is with 40. This is the initial one. And it's also dependent on lighting conditions. So later we use something called iterative thresholding to figure out what our right threshold should be, what we should take from the image.
Okay, I'll talk about this. All right, so when you get your initial image, this one right here, you can see how, well, this is actually a really good image, but normally you'll have some noise, you'll have a big blob over here and whatever, and so we have to get rid of that so we can isolate the pupil. So one thing we use is we use BW label, which is a built-in MATLAB function that groups together all the connected components, and we simply pick out the biggest one. It's actually really good on speed, but there are some disadvantages. Sometimes when the eye is near the corner is a dark spot in the eye, or in most people. So sometimes it can get skewed, or sometimes it can connect with the corner, so you have this oblong, weird-shaped pupil going, and that can reduce our accuracy on calculating the center. And also glare can be really bad, because if glare is just in the whole middle of the pupil, you'll maybe get 2 very small pieces on the side with the glare dividing the pupil in the center, so you don't have a completed circle. So that's a problem. You want this, or I can talk about it? You can talk about it. All right, so isolating the pupil is another somewhat built-in function using region props in the bounding box. When you have that largest blob, you simply just isolate it from the rest of the image. And the reason we do this is because if you have the original image, it's larger than this isolated one, and the later image processing can be kind of performance heavy, I guess, and we want to avoid that. We want the real time. All right? So we talk about the median filter.
Sure. So the next thing we do is we apply a median filter, and we used a 17 by 17 median filter, 2-dimensional, to filter out any salt and pepper noise. And also we found that glare spots, like this one right here, that could be easily eliminated by using the median filter, and our next slide, M-fill. So we use M-fill next to eliminate any holes of glare that might still be in the pupil. If you notice, this is a partial image of the pupil, and that's because our size algorithm took this to this distance right here, and that fell within our average size of the pupil. So what we do right here is the M-fill. I'll go next. The next thing we do is we apply a simple filter. We do -1,1 and then the transpose of -1,1 to find the vertical and horizontal edges. Then we use the Euclidean distance to find the largest length out of all these edges. And you can see it's plotted right here. This is the first point, this is the second point, and this is the midpoint. Now, when we initially tested this out, this midpoint would like float all over the place because what was happening is the threshold changes like every frame, usually. So what would happen is this would, go over here, over here, over here. It'd be sort of in the center, but we thought that we should do something to improve that performance. So to adjust the midpoint, we search within 40 pixels of the midpoint, and we look for the highest point on that. And that's usually not occluded because from our setup, the glare from the monitor was always at the bottom of the pupil.
I think it has to do with the fact that when you're sitting at the computer, your head's usually, or your eyes are above, I guess, the center point of the monitor, so you're kind of almost looking a little bit down on it, so the glare would be more towards the bottom.
Yes. If we were in a setup where the monitor was above, though, we would have to look at the bottom. But, I mean, it all depends on your setup. So after it finds its highest point, which is plotted right here, it goes down the radius of this largest one, and you can kind of see that. So the new point is right here in yellow, and the old one is in blue. And that is actually more accurate. It's less jittery than the old one.
Yeah, because I'll do this. All right, so now we're up to our iterative thresholding, and you saw the original image, but after this diameter is calculated, the size of pupil, it falls between a set range. So we can use that set diameter to change the threshold depending on the size of it or whatever. So if the diameter is too large, that means the image is including too much. So that white blob you saw is probably too large. So you're getting some of the iris, which is also dark. So we need to get rid of that. And if it's too small, you're probably only getting very small edge of the darkest part of the pupil. We don't want that either. So this iterative thresholding can stop that. And it also helps for different lighting conditions. So here's a good example. You see it starts off terrible. Like it's not getting anything close to a pupil. So as each frame goes, it's increasing the threshold by 3 or 2 or whatever number we have it set on till we get it pretty much constant. Now once it's set in that set range, it doesn't increase or decrease. Calibration?
Yeah, we designed a simple GUI to facilitate the process of calibration, and we'll explain that later, but basically what we do is we plot the 4 points of when the user is looking at the corners, and then we take the current centroid and we figure out where the user is looking from those 4 points. So basically what the user would do is click on the top left and then look at the top left of the screen for like 5 seconds and do the same with top right, bottom left, and bottom right. And then when all of those are recorded, you click start and it starts the program. Okay, and I'll explain this. This is our method for mouse control. You can see right here, there's 4 lines. And these are the distances between the current centroid, which is right here, and the lines on the top, the left, the bottom, and the right. Now, our setup had a slightly shifted camera. I can just show you. Because the curve of the hat kind of made it offset. So we had to account for that in our program. So what we did was we took this distance right here, and we divided it by the entire distance from here to here, and then we multiplied that by the screen size to get the current position on the screen. And we used a simple Java library to plot the mouse on the screen. So that wasn't built into MATLAB, but we had to use a Java library for that.
Okay, I'll talk about this. So one thing we were asked last time is what is the performance of it? Yeah, we were aiming for 30 frames per second, but it's MATLAB, it's slow. And so we did a couple tests. We actually took about 200 or so frames and averaged the time it took to get each of those frames. And the only thing that we could really take out was the median filter and the M-fill. Everything else was vital to the program, but this was just more of a, hey, let's make it prettier, work better. And you can see how we were getting average 8 frames per second. Okay. Where'd the other one go? And our last thing we implemented was blink detection. and it takes the median of the column vectors, and you see when it's open, there's a big difference between when it's closed. This, however, the threshold that we used is dependent on how large someone's eyelashes is. The larger the eyelash, the bigger this is going to be, because this is picking up the black of the eye. It's picking up the colors. And now we're going to do a program test, except we have to do it outside of PowerPoint. It's too awesome for it. This is actually me messing around with it.
Do you want me to start?
Yeah,
And then you can narrate.
I haven't started it. Did you press play? Okay. That's me starting the recorder. It's nothing special. Here I click it, and I'm focusing on the little dot right there, and then I'm looking at the four corners, and then I decide I didn't want to do that, so I shut it off. Then I open up MATLAB had better things to look at. So then once again I start at the point, and then I decided to try to focus on this hand right here. You can see where there is a little bit of error, but sooner or later I get it. There you go. All right. And then I go and try to look at the new file, and then I'm off to the corner, or that X, sorry. So there is a slight error, but I mean, once I stare at it long enough, it decides to finally go. And here I'm trying to look at the start bar. The corners are sometimes a little iffy due to the calibration on where I'm looking. Actually, when I calibrated this, I was looking at the wrong start, so it was a little weird. It was a little off. And then I went and checked the date, and then I was back to the center. So it is a little off sometimes, but what we found was if you kept your eye staring at the point, but moved your head just light movements, it would correct it and send it right where you want it. So I would say.
Let me talk about possible applications for blink detection for a second. So future work that could be done on this, if you had two cameras monitoring both eyes, or if you had one camera in a position that could monitor both eyes at one time, what you could actually do is create gestures for the user to interact with the mouse. Like if you blinked twice in your right eye, that could be right click. If you blink twice in your left eye, that could be a left click. 3 blinks could be like entering a scroll mode. That way you could scroll as if you were using a mouse. And that would make this very applicable to disabled people that can't move their head. Our target audience for this project was disabled people because we weren't going to be able to account for head movement in the limited amount of time that we had.
Okay. All right, future work, we were thinking, well, now we're out of time, but we can change it from MATLAB to something a little faster, C++ or something like that. We can definitely use smaller cameras. The camera on the hat's very bulky. It can get in the way. There are very small pinhole cameras that can do the same job. With the camera so close to the eye, one eye is focusing on the camera, the other eye is focusing on the screen far away. Take that hat off and just gives you a little headache. Any questions?
What screen resolution were you using in your computer? It seems to me that if you lower the resolution,
Well,
it would be more accurate.
we actually we thought about that too, and it was the complete opposite. When you lower the resolution, it like the jitteriness because of the pupil centroid changing becomes more pronounced, and that was why we didn't do that.
It's slightly more accurate. I mean, it all depends on your calibration data. I mean, our initial test with a lower resolution, we were in the middle of the project. We actually didn't run it with our final product right here. But I feel like if we did run it with a lower resolution or with something that had a much larger area, like if we were just standing right here looking at this projector, I feel like that would work much better.
It worked pretty good on the projector.
Yeah. Yeah, the larger the area
Yes.
and the lower the resolution, the better results you're going to get.
A lower resolution would also help because everything would be larger. Icons.
Right, that's
whatever.
exactly what I meant.
Yeah.
Like, there's fewer things to look at.
Exactly. Any other questions? Only one question?
Comments?
So you only tested with like one case, like only you tested on this, or maybe if some other students want to try, it seems that it is ready to do more
I mean, we can test with other people. With the iterative thresholding, I believe that it could work with other people's eye. That was the problem at first. We couldn't get the threshold correct for like someone with dark eyes compared to my light eyes, but it should auto adjust to anybody's eye, hopefully.
Yeah, and one of the papers we read was saying that the average size of the pupil is going to be pretty much fixed for any sort of person that uses our system. Any other questions, comments? All right, thank you.